With chapter 6, we're going to complete our discussion of the rock cycle for the first half of Geo 101. When you look at this picture, I think what's probably most striking is the banded rock formation that is also kind of bent here. And this is really characteristic of what's called high-grade metamorphism, which is what we're going to talk about in chapter 6 on metamorphism and metamorphic rocks. So the word metamorphism means to change, and it is a change in a rock from one rock to another in the solid state. That can occur at temperatures as low as 200 degrees Celsius and as high as about 700 degrees Celsius. Once temperatures exceed about 700 degrees Celsius, you start to have melting, and then you create igneous rocks. In general, during metamorphism, while the texture of rocks will change, the composition stays largely the same. The rock generally has the same chemistry as the parent rock. And the parent rock is also called the protolith. I usually use the word parent rock. Your textbook uses both. Parent rock is the rock that exists prior to metamorphism. That parent rock can be a sedimentary rock, an igneous rock, or any other metamorphic rock also. So it's a transition and a change in typically in texture, but sometimes a little bit in composition, meaning the minerals, not so much the actual chemistry of the parent rock. So there are a few drivers that cause metamorphism. Picture is just meant to illustrate that heat is actually a very significant cause of metamorphism. So the internal temperature of the earth is warm, and it gets warmer the deeper you go. Heat is important in metamorphism because it increases the rate of chemical reactions. And the warmer the temperature, as long as melting isn't occurring, the faster metamorphism will occur. And what will happen during metamorphism is recrystallization of crystals into fewer larger crystals. So crystals or grains from the parent rock will recrystallize into larger crystals. They will become fewer because they will merge. And so in general, as metamorphism continues, grain size also enlarges in metamorphism. The second big driver in metamorphism is pressure. And when we talk about pressure, we're really talking about what's called confining pressure. Confining pressure is illustrated here in this diagram. It increases with depth, but it's also true that it is equal in all directions. So here is a sequence of sedimentary rocks, and there's two enlargements here. There's one here, which is blown up in this portion here, and then there's a second packet of sedimentary rocks that's enlarged here. What you'll notice are these purple arrows. So the purple arrows illustrate stress. And the stress, you can notice when we're talking about confining pressure, is equal in all directions. And that's illustrated by the fact that these purple arrows are all the same size. What's also true is that if we look at deeper sections of this sedimentary rock, you can see that these purple arrows are larger. That illustrates that there's greater stress that's applied, which kind of makes sense, right? The deeper you go in the earth, the more overlying material there will be. So pressure will increase. So that's one version of another metamorphic driver. A third one is illustrated here. So before I give you the term for this, let's look at what's happening in this diagram. You can see that these pink arrows illustrate that there is convergence that's going on here, like a convergent plate boundary, which is where compressional stress occurs. And if we look at this packet of rocks, we can see that they've been folded tightly during a compression event. And if you look at the purple arrows, you can see that there's really only purple arrows coming from two directions, and that illustrates that there's been a squeezing of the rock in this region. So that is called differential stress. Differential just means change, and this is stress that is not equal in all directions. There are some directions, like in this case, the squeezing at a convergent plate boundary or the compressional stress at a convergent plate boundary, which is not the same as the overlying or underlying stress on this packet of rocks. The fourth way, then, that metamorphism can occur is when there are chemically active fluids that come into a region. So in this photograph here, where there's nothing for scale, here's a large garnet. So this garnet is probably about 2 inches, maybe 3 inches in diameter. You can see here's a second garnet, and then you can see there are blobs of hornblende here as well. And then actually, if we continue on in this line with the hornblende, you can see that there's more garnets that are in alignment, and these garnets here are also in alignment. So what can sometimes happen is in volcanic regions, there can be minerals that are transported easily by groundwater. So the groundwater tends to be hotter and more acidic, and it will basically dissolve minerals in regions of high stress, like either where you have a magma chamber or where you have a convergent plate boundary and compressional stresses are high. What'll happen is that pressure, that differential stress, will increase the temperature on the groundwater. The groundwater then will dissolve some of the minerals in the area of high stress. Those minerals will then get carried away by groundwater and, I went the wrong direction. And then when they move into areas of lower stress, maybe a little bit further away from the convergent zone, what will happen is those minerals will start to recrystallize, and they'll crystallize in these very large coarse grained minerals like you see here. And you can actually kind of trace where the groundwater moved when these minerals formed. So as that groundwater moved along likely an old fracture in the rock, first it transported the minerals, and the elements rather, in this hornblende until it got to this region, and then the hornblende crystallized here. It traveled a little further, the hornblende crystallized here, it traveled further, garnet formed, and then this garnet formed. So those are the 4 ways, the 4 drivers of metamorphism: heat, pressure, differential stress, and chemically active fluids. So this last one that we just spoke about, chemically active fluids, is really the only way that the composition of this parent rock will change, and that's just because you have minerals coming in from another portion of the region. The region of high stress gets transported, those minerals get transported to regions of lower stress. So because there are different ways that metamorphism can occur, metamorphism has been grouped into various sort of varieties. And by and large, the one that creates the largest volume of metamorphic rock is called regional metamorphism. So let's take a second and look at this diagram. So what you'll notice is, once again, these blue arrows, or these greenish, teal arrows, indicate convergence. Metamorphism is really common in areas of convergence. So what's happening is that when this portion of the plate is colliding, if you think in 3 dimensions, this portion of the plate is also moving in this direction. And same thing here. And throughout the entire plate boundary, you have huge areas where rock layers are being smashed into one another and compressed. So when that happens, a few things occur. You'll see that as a result of differential stress, you have folding of these rocks. You can see sometimes these rocks are fractured, and sometimes it gets so warm that you can have pockets of magma form inside the earth. The other thing you can see is that as you move closer to the region of highest, most intense metamorphism, the rocks will change. So if we start at our lowest point of metamorphism, what tends to happen is that we start off with a rock that forms called slate. Slate is a low-grade metamorphic rock. It forms for the metamorphism of the parent rock shale. You can see that they look very similar. And as you get a little bit closer, and you'll see this from your lab also on metamorphic rocks, as you get closer to that region of highest grade metamorphism, what starts to happen is those clay minerals will recrystallize, and they recrystallize into muscovite, and that creates this shinier rock called phyllite. Remember, muscovite is one that cleaves into those thin little sheets, and so that's what gives phyllite its shine here. As you increase the temperature and pressure a little bit more on the environment, so you move from this box to this box, more of those clay minerals will recrystallize, only this time they recrystallize into biotite, and you get the shiniest of the metamorphic rocks form, and that's called schist. Schist is composed again of biotite and muscovite, which are both of the minerals that cleave into thin sheets and are reflective because you see light bouncing off their cleavage plane. Then finally, if you increase the temperature and pressure on the setting even more, you form this rock. This is called gneiss. And gneiss is characterized by banding of minerals, where you have white minerals that sort of segregate themselves from darker colored minerals. They don't always have to be white. They can be pink. They can, I guess, be any sort of felsic color. But typically you have alternating bands of light and dark colors during regional metamorphism. And regional metamorphism typically occurs at convergent plate boundaries, where there's literally thousands of miles of area where those plates are converging, and compressional stress exists all along those plate boundaries. So we can see that when we look at the world map. So here's the world map, and areas where you have huge areas of convergence, especially continent to continent convergence, is over here. I keep losing my mouse, sorry. These are the Himalayas, right? And this is the Tibetan Plateau. So this whole area here is where you have India moving north and colliding in with Eurasia here, and it's uplifting the Himalayan mountains. Most of this regional metamorphism is going to occur, again, where continents are converging with one another because there's incredible compressional stress. And the most common place for that in our present Earth is the Himalayas. But if we kind of continue in a northwest trend, these are the Hindu Kush mountains, and they lead over to mountains in Iran and then Turkey, and then finally over into a series of mountain chains that we collectively call the Alps that extend pretty much from Turkey all the way up through Greece, Italy, Switzerland, and connect over basically to the Pyrenees Mountains here that separate France and Spain. But geologists sort of think of these collectively as the Alps because they're, again, caused by compression of continental land masses. And then finally, an ancient example of a continental to continental convergence zone is the Appalachian Mountains that they converged over 400 million years ago. So what you're really seeing here in the Appalachian Mountains in the eastern U.S. are just the stumps of mountains that have undergone hundreds of millions of years of erosion. If you've ever heard of Pangaea, Pangaea is a proposed supercontinent that existed before there was the current Atlantic Ocean. And if you were to kind of imagine that the Atlantic Ocean was closed, the Appalachian Mountains would extend northward into parts of the British Isles and Northern Ireland, and then up into Scandinavia, and then also would be continuous with this little segment of mountains. These are called the Atlas Mountains in northwestern Africa, and they used to form a continuous mountain range hundreds of millions of years ago prior to the breakup of Pangaea and the opening of the Atlantic Ocean. So what we see today are just the stumps of mountains that used to be as extensive and longer, in fact, than the Himalayas are today. So regional metamorphism is the biggest way that metamorphic rocks are created. On a smaller scale, we have something called contact metamorphism. So if you've ever been unfortunate enough to touch a stove or to touch something very hot, you know that you get yourself burned a little bit. And that's almost what's happening here in contact metamorphism. It occurs when you have a pluton or a magma chamber in the subsurface. And it comes into contact with rock that's already there. That magma intrudes its way up. And when it does, it's warm. And so it kind of burns the rocks that are around it. And when it does, it will cause contact metamorphism. It's the thermal alteration of the host rock. And also, magma chambers typically bring with them some volatiles. And those volatiles, remember, are carbon dioxide and water. So what happens is the magma chamber moves up, some of the water will carry minerals away from that magma chamber, and that's where you can also get those chemically infused rocks where you start to have those large garnets and hornblends form as water is coming off of the magma chamber and thermally altering the host rock or the surrounding rock. We call the area that is surrounding the granitic, the pluton or the intrusion, that's referred to as the metamorphic aureole, and it basically just illustrates the extent to which those rocks have been thermally altered. So, switching topics yet again, we're going to start to talk about some metamorphic textures. There are three main metamorphic textures, two primary ones, and then sort of a third accessory texture. And the most significant metamorphic texture that you will learn about is called foliated texture. Foliated texture occurs when there is visible alignment of minerals. Sometimes that alignment is more subtle, like with slate, and you have very small rotation of clay minerals, and sometimes it's very dramatic, like we see in gneiss. But typically what happens is that you have a rock, and this is supposed to illustrate an igneous rock, because you can see that the crystals or the black rectangles in this rock are very much randomly oriented. You can also see that this is under uniform pressure because all of these purple arrows are the same length. And then what can happen, foliation occurs under conditions of differential stress. So you can see that these purple arrows here are squeezing this rock together, and that the up and downward motion that is much smaller and unequal in strength to the left and right squeezing on this rock. So what begins to happen is you can see that these minerals begin to line up. So there are three things that occur to minerals during foliation. This is important. I usually ask about this on your second test, so put a little star on this. The first thing that happens is rotation of existing stable minerals. So if you have a mineral that is stable under those new environmental conditions, what will happen is it will rotate into this preferred orientation that you see here on the right. If minerals are unstable, though, they will recrystallize, and they recrystallize into minerals that are stable. They have the same chemistry, but they're put together, their crystal structure is different, so they'll be a different mineral, and they'll also recrystallize in this preferred orientation that we see in diagram B here. Finally, what will happen is that to other stable minerals, like for example, quartz grains. Quartz is stable for a lot of metamorphic conditions. So quartz pebbles that might be rounded in sedimentary rocks will become elongated and stretched out a little bit in metamorphic rocks. So you'll have a change of shape of minerals that are stable. So you can that's illustrated really nicely in this diagram. This is actually a white granite. Granite can occur in sort of pink or white varieties, but because I can see quartz grains here, I know this is granite and not syenite. So this grayish crystal here, that's your granite, or that's your quartz. So before metamorphism, this cartoon here illustrates how randomly the minerals are distributed in this white granite. And then after metamorphism, you have a situation where differential stress is applied, and those light and dark colored minerals will alternate in bands, and that's what you see here. And this is how granite can be the parent rock of gneiss, and that's something that you'll learn about in your lab as well. Okay, so this is a sort of famous outcrop in New York State. This is called the Snake, and this is a metamorphosed volcanic ash bed. This is up near like Gouverneur, New York, kind of close to Watertown. These lines that you see here, those are actually just from dynamite, where the road was blasted out here. This is the side of the road on, I think this is New York Route 11, where there's really a ton of cool outcrops. I'll show you some more in just a minute. But this grayish rock in through here, this is actually weathered marble. Marble flows really easily, which is cool, and you can actually see some of the flow structure in the marble here, but it's really the ash bed that stands out. But marble is an example of a rock that has non-foliated texture. It's a metamorphic rock that lacks any foliation. There's no visible alignment of minerals. Typically, it occurs when rocks are minimally deformed, so not usually a ton of compression. It also occurs a lot of times with contact metamorphism as well. So this is a little bit further down New York Route 11. This is called the Marble Funnel, and this is a basalt rock layer, and then you have some upward motion along a fracture of some marble. It's really cool. Here's one of my old students, Sean, with a rock hammer standing next to the marble funnel, so you can really see how big it is. So marble is an example of a non-foliated metamorphic rock. The other one that you typically have in lab is quartzite. The difference is the parent rock for marble is going to be limestone, and so it'll react to acid because limestone has calcite. And then quartzite has a parent rock of quartz sandstone, and so it won't react to acid, and it's harder than glass. All right, your third metamorphic texture is that didn't show up. Yes, that typically, as I just mentioned, non-foliated rocks are composed of just one mineral. So, for example, marble is primarily composed of calcite, and quartzite is typically composed of quartz. All right, this is a little bit hard to look at, but I really like this picture of the garnet here. You can see again there's kind of a string of minerals that are aligned along this general path right here. This is a quarter that I used for scale. I don't just always take pictures of my change, but there we are. So this is the way that garnet usually looks in New York State. Garnet doesn't always look this way in New York State. This one is maybe an easier picture to look at. This is like a purple garnet. This is really cool. So to go back to the unpleasant picture for a second, this garnet is common in the Gore Mountain region, which is like North Creek area in the Adirondacks. Also in the Adirondacks, but a little bit, I guess, further south are these garnets. These are sort of purpley garnets, and these are found outside of Lake George, New York. And again, I really like this picture, first of all, because you're not blinded, but secondly, you can see the alignment of these garnets. It's really cool. It's very fun. And garnet is really what stands out the most here. This is called porphyrioblastic texture. Porphyrioblastic, that word should remind you of the word porphyritic, and that's because porphyritic means multiple grain sizes in an igneous rock. Porphyrioblastic means multiple grain sizes in a metamorphic rock. Those large crystals of garnet are called porphyrioblasts, and they're in a finer grained matrix. This is not a fine grained rock, but it's finer in grain size than these garnets are. And here's another giant picture of some garnet from New York. New York State used to produce like 97% of the world's garnet. Most of those are in the Gore Mountain. Oh my God, I just forgot about this guy's finger. Oh, sorry, I apologize. That was distracting to me. So there are places that you can go and still collect some of these huge garnets. There's something called the Barton Mine in the Adirondacks, and I think it's like $10 to get in, and you can mine garnet. Or if you go a little bit further up the road at the Barton Mine, there's an this sounds ridiculous, but there's an old ski lodge, and if you ask the people at the ski lodge, they'll give you directions to an old quarry that's further up the hill in like the woods, but there's an old quarry where you can collect all of the garnet you want for free. So that's exciting. All right, so I used the term metamorphic grade earlier. So we have to kind of infer what temperatures and pressures metamorphic rocks form at, because they almost always form inside the earth. The only time they form on the surface of the earth is if there's like a meteor impact, which is thankfully not very common. So we can use different tools to figure out if a rock forms at sort of what's a low grade metamorphism, like 200 degrees Celsius, an intermediate grade metamorphism, or a more high grade metamorphism up to like 800 or so degrees. Again, after 700 or 800 degrees Celsius, rocks will melt. So here are your foliated metamorphic rocks. They start with no alteration, so this would be like a shale here. And then as you increase temperature and pressure on shale, it turns to slate. You increase temperature and pressure on slate, it turns to phyllite, and phyllite will turn to schist. Schist will turn to gneiss. And then shortly beyond the temperature and pressure where gneiss is stable, you have rocks begin to melt. And then there are these fun minerals that are typically associated with metamorphic rocks. They're called metamorphic index minerals. And they're useful because they tell you a little bit about the temperature under which these rocks formed. So, for example, in slate, phyllite, and some of schist, you can find a green mineral called chlorite. And you can kind of go from the green coloration here and read down to the bottom, and this will tell you at what rocks you typically find chloride in. And chloride is stable. It first becomes stable about 200 degrees Celsius, and it probably stops being stable around like, oh boy, here we go with math, about 500 degrees Celsius or so. Muscovite is not stable to like 250. So when you see muscovite, you know you're at least looking at temperatures of 250 degrees and up. Biotite maybe a little bit more. Higher grade metamorphism. Now we're in intermediate to high grade metamorphism, and that's where garnet is found. So you've had muscovite, biotite, and garnet in your lab. Staurolite is a sort of reddish colored mineral that's only stable from intermediate to high grade metamorphism. And selimanite is a variety of mineral that really is only stable in high grade metamorphism. So if you can identify selimanite, which you could if you took a mineralogy class, then you would understand immediately that you're looking at a high grade metamorphic rock. So then down here, you also have these two minerals, right? You have the feldspars, which include a whole bunch of minerals like orthoclase and plagioclase, and then you have quartz. And you can see that these two minerals are not good index minerals. They don't narrow down at all the temperature that your metamorphic rock formed at, because they are stable from low to high grade metamorphism, so they're less useful. That's the end of chapter 6. You're going to spend a little bit of time doing an exercise now, not only reviewing some of your metamorphic rocks from lab, but then also spending some time looking a little bit deeper into that index mineral chart. Have a good time.